Okay, welcome back. It's our last talk for today, and it is by Shvydkoy from University of Illinois, Chicago. And the talk will be on generic alignment conjecture and the problem of emergent collective behavior.
Right. Well, first of all, thank the organizers for so kind invitation to this very nice meeting. When selecting the topic for this conference, I was thinking how to make it more related to what Alexis did. And I realized that it's actually very easy. You just do what you do. And, and most likely you will find interaction with Alexis' research. And indeed, my familiarity with Alexis' results came through the study of regularity problems for models that arise in the subject of collective behavior. So let me we all seen these pictures of flock of birds and school of fish. So there's no need for me to put that out. So I'm going to start with a little bit more mathematical motivation. The motivation came from what is known as Reynolds three-zone model. This model of basic interaction between birds. That's where it's originally stated. To program into computer code, which was used to make realistic simulations of flux for movie production. Okay, so he actually published this paper here. He outlined these three principles of interactions. So you have a repulsion. You have local alignment around some zone of alignment around every bird, and there is a zone of attraction. And so if each bird has these three forces, then the flock will behave more or less realistically. That was indeed true, and he even got the Oscar for this. Okay, not the usual science award, but the Oscar for technical contributions. So. So this is still actually a three-zone model is actually extremely difficult because it doesn't have any natural steady state. But it raises the question of understanding the issue of emergence. So how patterns or just simply alignment can occur from local interactions between agents. And so typically the agent-based system, the system of ODEs, involves this kind of alignment force where this bracket means some kind of environmental averaging. Okay, we're going to see some examples later. So some kind of averaging of velocities around the neighborhood of each agent, and SI encodes the strengths of that interaction. Okay, so what we expect is that if this interaction is local, then initially sort of chaotic configuration will start to emerge will start to result in some local patterns, and these local patterns upon further interactions will result in some kind of consensus. Okay, so this is kind of a very phenomenological idea behind emergence. To put it in more maybe precise mathematical terms, what we're going to look at is mostly Cooker's-Mail alignment model. So this model was introduced in 2007, relatively recently, actually, in response to obtaining a model which would give this kind of alignment results unconditionally, based on just some assumptions on the communication kernel, and not about any connectivity assumptions for all time. So this model here has the communication embedded into this alignment protocol. The communication is kernel phi, which is typically just radially decaying kernel. Typically non-degenerate. So if you write in terms of my notation on the previous slide, then this is the kind of averaging you get. So it's kind of kernel weighted averaging. And this is your strengths. So all contributions of interactions between agents centered at xi. Because the kernel is decreasing, if agents are far away, they're losing communication. And so the question becomes whether or not the flock will have enough strength to spread out, or maybe the communication will keep it close together and align. So the story starts from the Hooker-Smell theorem, who actually gave a criterion of how fast the kernel has to decay, or how slow does it have to decay in order to ensure flocking. Okay, so they actually looked at this particular power law kernel, and they showed that if, as long as the tail of this kernel is not integrable in radial variable, then the flock will align exponentially fast, and it will remain bounded diameter. So it will remain compact. Later on, Ha-Tadmor and Ha-Liu produced different proofs, and it turned out that, in fact, you don't need that particular power law. You can actually work with any fat tail kernel. So any kernel phi which is decaying and non-integrable. Right? So it's quite general result. It was also extended to kinetic formulation by Correa, Farnese, Rosati, Toscani, and to hydrodynamic system by Tan and Tadmor. So I'm not going to say too much about applications of this model. Just want to focus on mathematics and also on the survey of results around this local emergence problem. But let me assure you that these alignment models appear in all various kinds of contexts: satellite navigation, feedback control problems, even in numerical simulation and machine learning technique has been applied to read off particular shapes of the kernel given the data. So they turned out to be singular, but there are a lot of applications of this to the various problems. So let's come back to this local communication. Now, this is the question we're going to stick with. Okay, we're going to assume that the kernel is completely local. And so this thesis that local communication implies flocking commonly requires some kind of propagation of connectivity. Because let's say if we are in an open space, I can easily just put two separate flocks directed in the opposite directions. They will never communicate. They will never have a chance to communicate, right? So some kind of, in the open space at least, without any other additional confinement forces, one has to assume some kind of propagation of connectivity, and this was indeed formalized by Morales, Plejik, and Tadmor. Or alternatively, you can assume that initially your flock is graph connected, but the communication strength is very, very high. So in that case, the flock will not even have a chance to disperse and will align almost instantaneously. Okay, so connectivity is an assumption for all times. It's really not something that we can check, right? So it is desirable to actually look at the results which do not depend on the connectivity assumption. And one of them is, for instance, if you look at, by Tadmor and Shu, if you look at the confinement, so another confinement force you put in the system, particularly the quadratic confinement, then the condition on the communication kernel relaxes to something like 1 over r squared, right? But somehow, even if you put higher power here, it doesn't relax too much either. So I mean, it's really a very subtle result connected to this to this particular decay. Nevertheless, it does improve, but it's not local, right? So the kernel still has to be global. So there are essentially 3 attempted approaches to this problem. One is I will describe next on a microscopic level. We will talk about the periodic torus. So I would like to, I can either put confinement forces, but then the corresponding conjecture will change. So the periodic settings is the most easy to understand, formulate mathematically. It also avoids the issue of dispersion at infinity. On the kinetic level, alignment becomes the problem of relaxation, convergence to Maxwellian, if we put a little bit of noise. the motivation for putting a little bit of noise will come from understanding generic alignment conjecture as well. And on macroscopic level, we can look at another concept of connectivity, but in terms of lower bound on the density, okay, which is something that people usually do. It's not in some cases we can say something definite about this particular setting. So let me start with just a discrete agent-based system. So let's assume that we're looking at Hooker-Snell system on a torus, right? Now, unfortunately, if your communication is local, I still can produce counterexamples. They're actually quite simple. You just put one agent on one geodesic and one agent maybe on a parallel geodesic, right? Just a little bit far, but with different velocities. So they will never align. Or you can even put them in sort of perpendicular way. If the velocities are mutually irrational, they will also don't come close to each other. Okay. So what are these examples? These are all examples of very special solutions, right? They actually form measure zero set. In fact, there is a Kronecker criterion, which is very well-known result in ergodic theory. So if agents don't interact, then their trajectories are Euclidean lines, okay? Periodized Euclidean lines on the ensemble torus. So I'm going to put all these positions in one variable and all the velocities in another variable. So I'm going to look at it as a sort of ensemble couple, right? So if they don't interact, they don't feel densely the torus. And in fact, what they will feel is the k-dimensional subtorus with the dimension equal to the rational dimension of all the coordinates of the velocities over the field of rational numbers. Right? That's the exact actually statement. So in any case, if case less than n, then that's a measure zero set, right? So here's the conjecture. For almost every initial data, solutions to Hooker-Snell system will align. I mean, it's quite natural, right? As long as you avoid these special solutions, you should align. That's an open problem, the way it's stated. But there has been some progress. So first of all, with Helge Dittert, we did that in dimension n equal 1. Now, that's actually sort of, we did something else, but as a consequence of the method, we could prove it for this particular case for n equal 1. The idea is quite clear. I mean, it's just to geometrically restrain, right? If you're not aligned, you will still meet somewhere, right? You don't have these locked states as in two-dimensional torus. So you meet, you interact, you align. If you don't align yet and you disperse, you still meet at another end, and you keep going until you're aligned, okay? So your rate of alignment, though, will suffer. It's not going to be exponential. It's going to be some kind of algebraic at best, because you will have these long transient periods of non-interactions. Okay. The conjecture is true for sticky particle model. Now, sticky particle model has a memory of the initial condition. So if two particles interact, or two clusters will come together, they will travel together with the average momentum, right? So if your initial velocities have been rationally independent, right? They come together. That's just the rational combination of the previous ones. They will still be rationally independent, right? So if at the end of the day you have two or more clusters which do not align, they have to be rationally dependent, and that's a contradiction. So there's just a strong memory of rational dependence coming from initial condition. So it's just a simple result. What's not so simple is the following. The conjecture is true for two agents. Okay? Actually, in any dimension. It's actually a consequence of more general result. For any n, and for almost every initial data, there will be at least two agents that will align. Okay, and let me explain how this is done. So this is coming from the statistical mechanics point of view on the system. So the alignment means that the velocities converge to the diagonal. So in this big ensemble space, that's just a measure zero set, right? So a prerequisite for alignment would be that my semigroup, sorry, S of t is just the flow of the system of the ODE that I'm studying. The prerequisite for alignment would be the shrinking of volumes to zero, right? Because this is volume 0. That's not, unfortunately, necessary and sufficient condition. If it were, that we would have been done. But at least we can try to prove that the volume element of this flow goes to 0. So if you look at the Liouville formula, actually you can write down explicitly what the volume element looks like. It's just the integral of this all these interactions between the agents. And so in order to prove that it goes to 0, I have to prove that this integral inside goes to plus infinity, right? Okay, so if there is a region where it doesn't go to plus infinity, there's some bad set which does not shrink to 0, right? Then it will remain under the flow method. It will have a finite mass. It will not, right? It will not shrink to 0. It may vary. Actually, it will decrease because it's an entropy. It will decrease, but never go to 0. If it never goes to 0, then you can apply Poincare recurrence. So this blob will come back into itself infinitely many times, right? In fact, almost every agent in that blob will come back to the same region almost infinitely many times. But because it's a set of positive measure, it has to stay away, at least part of it will have to stay away from those locked states, right? So that means that the agents will have to interact, right? They will at least one pair of agents will always have to come together at a certain distance. What does it mean in terms of this? It means that this phi xi minus xj will be bounded away from 0, at least for some short period of time. But because there are infinitely many such times by Poincare recurrence, it results in infinite integral, right? So this argument implies that if I look at this total sum of all the interactions, it will go to infinity. It will not be integrable. So it means that at least one of them will not be integrable because there are only finitely many of them. And that's that exact pair of agents that will align. So there's been another lemma to be proved that if that particular interaction is not integrable, then it will result in the alignment of that particular pair. So basically, that's the idea. So let me now go to other descriptions, kinetic and hydrodynamic. There is a little bit of story to be told here. First, looking at mean field limit of empirical measures, you obtain velocity alignment model, the corresponding with the corresponding alignment force. High and Tadmor first derived it formally, then Ha and Liu actually justified it. Here, the corresponding averaging operator and the corresponding strength functions are stated in terms of macroscopic quantities. So, for example, for the Cooker-Smale system, it becomes sort of this ratio of convolutions. So the momentum convolved with phi, sub phi means convolution with phi. Phi is the communication kernel divided by rho phi. So those who study non-homogeneous turbulence realize that this is what's called the Favre filtration, right? So Favre filtration, if you look at the continuity equation, the modified density will also satisfy continuity equation relative to the Favre field. Moch-Tadmor model is another variant of these averaging models where the strength is assumed to be equal to 1. That's the only difference. But what's interesting is that this model takes care of various anomalies that are present in Cooker-Smale model if you study flocks of different sizes, like in multi-scale sizes. There are other models you can think of. You can over-modify Favre filtration. That will be another averaging. There's actually a whole ecosystem of these operators called environmental averaging. And in this paper here, we developed sort of kind of a functional analysis behind this, and also the properties of these models that come from functional properties of the corresponding averaging operators. So if you go further and look at the hydrodynamic description, then this is how it's going to look like, the equation for the density and the momentum. Unfortunately, of course, you have a closure problem, the Reynolds stress tensor, and in various ways you can close it. by putting some additional forces into your kinetic model. So there were two regimes which have been studied. One is monokinetic regime by Kahn and Vasseur for sort of all-to-all interaction model. Figali and Kahn took care of the full Cooker-Smale, but with the assumption that the limiting density is non-vacuous, and I removed that assumption recently. So it converges to monokinetic ansatz, and in that case, you obtain the pressureless Euler alignment system, which is actually the most studied system in this context because it kind of allows for a variety of collective outcomes. So you still do expect the velocity to align to a constant in a long time, but the density can be anything. It can be any traveling patch, right, with that average velocity. Another regime, though, the Maxwellian, when you force your kinetic equation with Fokker-Planck, it saturates to local Maxwellian, and that results into isothermal system. Here, though, the natural steady states are uniformly distributed densities, right? Because if everything here is zero and you still have a gradient of rho, it has to vanish, right? So the density has to be uniform as well.
Temperature is specified in this Maxwellian.
The temperature is that's where it's because the way you force it is with the Fokker-Planck operator, with the constant in front of the Laplacian. Yeah, maybe you can force it with more sophisticated temperature laws, but it hasn't been done. So the regularity of these models has seen some progress in recent years. Basically, the upshot of all this is in 1D, we understand things pretty well. In 2D, we know things blow up, or look for smooth kernels. For singular kernels, it's an open question. So in 1D, there's actually a precise threshold criterion for global regularity, stated in terms of this quantity E, which is Ux plus something plus the convolution of rho with phi. So if it wasn't for the alignment force, it would have been just the Berger's equation, and the regularity would be Ux is positive, right? That's where the characteristics don't overlap. But the alignment force has some kind of regularization property, even with four smooth kernels. So therefore, you have a little bit of a leeway, right, for your initial condition. This quantity is actually conserved, and it's related to what's called Brèche-Desjardins entropy, in the way that Brèche-Desjardins has two parts. It's his kinetic and potential part, right? So this is the derivative of the kinetic part. Okay, and this idea actually behind this analogy with Brèche-Desjardins goes much further. I'll comment on it a little later. If the kernel is singular, then you're looking at fractional Laplacian. So this is where Caffarelli and Vasseur comes into play. They proved a general result for linear fractional parabolic equations with bounded drifts. We found it useful for regularity of the system too. Doh, Kiselov, Rizhik, and Tan had a different approach with modulus of continuity. Nevertheless, we can cover the entire range of alpha from 0 to 2. So in multi-D, however, the situation is much more complicated. So some spectral dynamics gives you some small initial data in 2D. There are some special solutions which exist globally, like unidirectional flows, which have also the same conservation law. Chang-Hu Tan looked at radial flows, and then Dan Chen, Muha Pezhik, Wroblewski, and myself, we proved small initial data for singular communication kernels in multi-D. Okay, and for the isothermal, really there is not much. So we know small data, Choi 2018. And then Konstantin Drivas and myself, we did global well-posedness for non-vacuous solutions through this idea of connection of this quantity to the Brèche-Desjardins entropy. In fact, this is sort of like tier. So Brèche-Desjardins is like tier 0 entropy. This is tier 1, but it's actually the whole hierarchy of entropies you can look at. And the interesting thing is that the Brèche-Desjardins potential part of it controls. It controls the power of density, right? Turns out that the first tier already controls the derivative of the density. The second tier controls the second derivative, and so on. So you can go up the tiers and you control higher order of the derivative. So you can develop regularity theory just based on this hierarchy of entropies. Okay, so let me come back to this phenomenology of alignment, right? Regularity questions are of course interesting, but we're looking at long time behavior. So if I just for a moment focus on pressureless Euler alignment system, okay, there's no pressure. This is conservation momentum with the alignment force. The first thing you look at is the energy, right? What's the energy law? Well, the energy law, the energy dissipates, right? It works like an entropy. It won't stop until you're aligned. But the question is, so if communication kernel was global, I would have easily connected this dissipation back to the energy, and I would have obtained exponential decay of the energy. By the way, we can assume that by Galilean invariance, we can assume that the total momentum is equal to 0. So alignment means going to 0. Okay. So otherwise, I'm looking at this term here, which I can represent as the scalar product of a certain alignment operator, which is this operator here, with U. Okay. And so I can basically say, okay, I can replace this with the energy, and what's the price that I'm paying? I'm paying this a price lambda, which I can state in a variational form, right? This is basically the second eigenvalue of this operator, L. So if that eigenvalue is non-integrable in time, then I'm done, okay? So question is, how can I estimate this lambda? So the result that we kind of knew, it was always in the air, is we need lower bound. So here, rho minus is the minimum, rho plus is the maximum of the density. So we knew that it should be like 1 over square root of t. So Eitan formalized that in this formula. So lambda is like rho minus squared divided by rho plus. Unfortunately, it depends on rho plus. So if we knew that rho plus is under control, then we would have concluded that if rho minus is like 1 over square root of t, then you're aligned. So how do we get rid of this assumption, and can we even improve this, right? Because in fact, we never know a priori this estimate. Okay, so let's address these questions separately, because the answer actually would be useful for other things. How do we get rid of rho plus? So the idea is not to. So the way you obtain this formula is you multiply this equation by u, and then you symmetrize, right? That's what we always do in this business. We symmetrize. Now this is a curse here. You should not symmetrize. Let's just keep them separately. Okay, keep them separately. What you see here is kind of like the difference of two energies. One is this strength-weighted energy, and the other one is also sort of energy. It's a non-negative term, okay, and it scales like energy. So I'm going to call them E1 and E0. Okay, E0 is actually related to the true physical energy by if you just replace the strengths back with rho minus, then you just lose, you pick up another rho minus, but rho minus is not rho plus, so I'm not concerned about rho minus. Okay, so if I can prove this kind of coercivity or spectral gap condition, E naught minus E1 is bigger than epsilon E naught, then I would have obtained something in terms of epsilon here. So lambda is epsilon rho minus, and the question is, can we find a bound on epsilon independent of rho plus? So unfortunately, if you work with this top tier two energies, it's difficult to do. I mean, you always run into this rho plus computation. Turns out that there's another hierarchy. You can look at other low tier energies. So the next one would be average. The next one would be average, double average. The next one, double average, and so on, right? Turns out that it's a monotone family of energies. And even the difference between them is also monotone. So instead of looking at the difference between the top tier, I'm going to look at the difference between the lower tier, the next tier energies. That's why it's called low energy method. So we're going to low tiers. So it turns out, just by operator formalism, you can show that if you have a spectral gap on the lower tier energies, it implies the spectral gap in the higher tier. In fact, for symmetric models, it's even equivalent. So it turns out that estimates you obtain from this lower tier coercivity estimates become independent of rho plus. And in fact, for many of the models, we can write down explicit formula for this difference, and it looks very very interesting. Let me just give you an example for the cooker snail. So this is how it looks like. Okay. I forgot to mention that we need to assume that the kernel is Bochner positive. This is just needed for the basic positive definiteness of the averaging operator. Without it, we have no hope. But it's not really very restrictive. I mean, if you look at if the phi is a local kernel, then psi is also going to be a local kernel with the support just twice as wide. But it's just as local as any. So it turns out that it has this very interesting, perplexing formula, which involves this Fabre filtrations of relative to this intermediate kernel psi. But what's interesting here is that you pick up a lot of densities as a weight, and there's one density that comes on the bottom, rho sub phi. Okay, so normally if it was just rho, I would be forced to replace it with rho plus, but it's a convolution with phi, and phi is a smooth kernel, so it's always bounded from above. So you no longer need rho plus, although you pick up now 1, 2, 3 densities instead of 2. So you traded the power of density 2 by actually 4 powers of densities, but your advantage is that you're no longer using the rho plus. So the formula actually becomes worse. It's 1 over square root of 4, but it's independent of rho plus. And this is the spectral gap computation that I will remember for my next part of the talk. Okay. Now this is actually going to be very important. Now, but let's stick with the hydrodynamic settings for a second. Can we in fact improve this 1/4 or 1/2 without sacrificing any other assumptions, without imposing any other assumption on the density? And it turns out that yes, we can do that, but we have to modify the model a little bit. In fact, in a lot of these biological observations, people notice that in a lot of these flock systems, the birds, they don't really feel the Euclidean distance. Okay, so the kernel, so far in my case, the kernel was a function of Euclidean distance between x and y. What they do feel though is the density. Okay, so the information will spread faster in a thinner sections of the flock than it would in a thicker, just because you have to communicate with more agents in those directions. So how can you build it into the actual kernel? So we had a version of this. The models that are based on this density weighted distances are called topological models. Typically, these are the terms that biologists are using. So we proposed one of these topological models. So what you do is you look at 2 agents x and y, and you fix some communication domain between them. It can be any shape of domain. We just for the purposes of this picture, I just drew something, but it has to be x-symmetric, and it has to be mirror symmetric, and the angles, the sectors at x and y have to be of opening less than pi. It's a technical assumption. Okay. So every pair of agents x and y communicates through this domain. D x, y, t is the mass of this domain. Okay, this is my kind of distance function. So I'm going to build this into the kernel. So for fractional Laplacian, this should have been x minus y alpha plus n, right? So this scales like n. This scales like x minus y n to the power n because it's the volume, right? So instead of using the metric volume, I replace it with the topological volume, with the density. And this becomes a new kernel. Okay, it's local, but it actively depends on the density inside. So it turns out, so this is the topological Euler alignment. It looks exactly like Euler, like pressureless Euler alignment system, except we've used this topological kernel. And it turns out that you need 1 over t. Okay, so once you include all these topological effects, you go down to 1 over t, and you even get a rate of alignment, something like logarithmic. But of course, that's because your local is kernel, and you have this transient, periods of weak communication. So this is kind of as close as we can get to vacuum. And it turns out that in 1D, this is not an assumption. That is actually true a priori. So this is what we can prove in 1D. Okay, so if you're in multi-D, it's still an assumption. So in 2D, or in multi-D, we cannot prove that, but in 1D, it is a theorem. So so that's the best we can get, and the proof actually does replicate this phenomenological picture that I showed in the beginning. Yes.
Is the 1/6 sharp?
By no means not. Well, this is what came out from just the proof, but I don't think it's sharp. Okay, probably one can do something better if you work harder on it. Let me just say that it's interesting that, and I learned the Georgi method from Alexei's works, of course, and this was seated in my mind when we were doing this model, and it turns out that what you actually do is the first de Georgi lemma. Okay, because the first de Georgi lemma, it tells you that the dissipation burns energy, right? It burns energy, and you can prove this locally around the extreme values. So the Georgi lemma shows you transition from L2 to L infinity, right? You can quantify that transition in this context near the extremes. And you can show that near the extremes, you get local alignment. Okay? Then it turns out, using Moret-Campanata spaces, you can show that all across the domain, there are local alignments happening. Okay? You can connect that local alignment to the dissipation of energy there. And then, because you're the torus, you're connected, these pieces start communicating, and then you connect the two extremes. So, and you obtain this. Unfortunately, only log to the power 1/6, but again, we didn't work too hard on it. Could be better. Okay, regularity theory here, I'm not gonna even talk a lot. It's technical. It's technical subject. Simply because the kernel is active. It actually depends on the density. Density is on the bottom. So even doing local Wilposeness involves some product estimates and things like that. So this was done in collaboration with my students and postdocs. So let me switch to, I should watch time, right? Okay. So let me switch to the third part, or third approach to this generic alignment conjecture. So one natural way to break those locked states is to introduce a little bit of noise. Right? The noise definitely will vibrate those trajectories, and they will not stay as sharp as they are. So the particular way we put the noise there is we put the strengths in front of Brownian motion, simply because we want to make a noise where the flock is, right? It's kind of a material noise. In the corresponding mean field limit, you obtain the Fokker-Planck equation here, and the strength function, of course, that was in front of the noise turns into a coefficient in front of the diffusion, right? That's actually part of the problem, because if there's vacuum, that becomes degenerate, right? But still, we would expect that the long-time behavior of solution to this Fokker-Planck equation would be relaxation to the global Maxwellian, right? If that's the case, if we can prove that, then we can understand alignment in the vanishing noise limit, right? Once you have Maxwellian, then you set another limit as noise goes to zero, and of course the Maxwellian concentrates on the Dirac in this case, and Dirac means alignment. Okay, so this is another sort of parallel with the turbulence theory. This is how you understand the laws of turbulence. First, you let time go to infinity, let your trajectory settle on the attractor, and then you study statistics on the attractor in the vanishing viscosity limit. That's exactly what we're doing here, except that our attractor is just one point, the Maxwellian. So the same philosophy. So this program has seen a partial success. Back in 2010, Duan, Fornazi, and Toscani proved this result in perturbative settings. So if you're already near Maxwellian, Choi proved the same result for a model with purely local alignment. Okay, it's not Cooker-Smale, but purely local. Still interesting model because this is what we force, in fact, in the monokinetic regime. So it's good to know that it relaxes. And these results were the techniques that they used is based on the linearization and spectral gap. So it's kind of very inspired by the corresponding results that appear at that time for collisional models. Okay. So to push it further, we needed to do something else. So let me just state the result. It's actually true. So if you look at particular Cooker-Snail model with this strength function, rho phi, and you assume that your kernel is Bochner positive, first of all, your model is going to be well posed in the corresponding weighted Sobolev spaces. We are in the torus, so the weights are only in V. Okay, that's the only thing we need. And what happens is that for any positive time, the lower bound of the density becomes positive uniformly for all time, and the solution relaxes to the Maxwellian in L1. Of course, in the relative entropy sense as well, but it implies L1. It relaxes with this particular rates in terms of noise level. I'm not sure if these are optimal. We didn't do any kind of enhanced dissipation analysis, but this is just what came out from the hypercoercivity estimates. So I'm just going to say a few words about the proof and why is it related to that lower energy method. So there are three main ingredients here. Well, actually, global oppositeness is another ingredient, but let's skip it. Uniform gain of positivity. This is very important. This is something that were known effect, of course, in this kinetic models, but we have to establish this Gaussian tails uniformly in time, right? Because if we do that, then the density, if you just integrate this Gaussian in V, this is pointwise in X and V, n time. Okay, so if you integrate in V, then you just obtain a constant. So then your rho minus becomes bounded away from 0. Then your spectral gap becomes bounded away from 0 because it's independent of rho plus. So this is why we didn't really care about what this power is. As long as it's bounded from below, that's it. And then once you get that, you can apply the hypercoercivity. So I'm probably not going to say too much. Let me just say that the hypercoercivity part is actually the Villani-de Villiers scheme. So you look at this form of A star, A, B, transport diffusion form of your Fokker-Planck, but there is this additional alignment force that comes from the alignment. You write it in terms of this normalized distribution, and you look at the relative entropy. Here there are two forms of entropy law. Okay, one is non-dissipative, so both are useful. One is non-dissipative. You have your Fisher information, but then you have the junk coming from the alignment. And another form is you sacrifice dissipation from higher order, but you have difference of energies. Okay, so this is where the spectral gaps come into picture. If you apply the spectral gap, this becomes less than epsilon times the energy. So if you combine the two forms of your entropy inequality, it kills this residual part, and it becomes completely. Actually, you gain both. You have the cake, and you eat it, right? So you have the Fisher information and the energy and the alignment energy. Okay. Then you insert all the other cross product information and information in X. You write the equation for all of them. It turns out, because the alignment force is non-linear, right? It's bilinear. So you don't usually expect that it will work unless you assume something, smallest assumption or something like that. But it works globally for any data because of some special constellations. And in the end of the day, you obtain Gronall inequality and you have exponential decay. If you do this carefully, those sigmas to the power 1/2 will come out in a calculation. So the spectral gap I already explained, so let me skip that. Let me just say one last word about this gain of positivity. So this is not a new effect. Of course, we knew that since Kolmogorov. For Kolmogorov equation, you can just write down the fundamental solution. You can see it explicitly. Villanidi-Villet did it for space homogeneous Fokker-Planck. But when you go further, it becomes kind of tricky. For Boltzmann and Landau, this was done by Henderson, Snelson, and Turfulet. And for the closest to our model would be the result of Ansecchi, Ansecchi, okay, and Zhu, who did it for general Fokker-Planck equation with bounded drift, but it didn't apply to our case in out of the box. Okay, we have to do something else, and all of these results, unfortunately, produce Gaussian bounds that depend on time. So they actually deteriorate on time because they depend on smoothness of your data. So if you start at some time t, you rely on some smoothness for your initial plateau construction. For us, this is bad because we don't control regularity of the solutions. We don't even control the infinity norm of the solution. So we had to do something else. And the tool that came very useful for us was this recent result of Jessica Girard and Cyril Lambert with weak Harnack inequality for super solutions. So when you look at the strength, when you look at the alignment term here, and you sort of distribute your derivatives, you get something like NF plus, all this multiplied to V. So this is kind of the term that can be handled by these general results. Okay. Now here we have F, which we do if we treat it as a source or as a force. We have bad constants in the Harnack inequality because we don't control the size of this force. Okay. So instead, what we do is we basically forget about it because it's positive, and we treat this as a super solution. Okay. So for super solutions, you don't have Harnack inequality, but you have this weak Harnack inequality, which turns out to still work for us, because really what you're looking at is kind of to spread positivity in V direction. You start with some initial plateau in your kinetic box, okay, which you still have to kind of choose carefully because essentially what these constants depend on is the initial entropy. That's it. And the entropy is controlled in time globally. So you just have to be careful with how you choose these boxes and how you choose your plateaus. But at the end of the day, if you do it carefully, you do the iPad trick, right? You do the iPad. So you scale all to size 1. The magic about rescaling is the diffusion doesn't change, but the drift gets even smaller. So once you zoom in, right, your drift becomes better. And then you try to, this is your plateau. You apply Gerand Imberg weak Harnack, and you obtain completely support from below if you wait a little bit, right? So that's your much better plateau than the initial one, and then you have to spread it into V directions. So you do it by constructing. You're starting from this box, and you construct Harnack chains. Okay, the way these Harnack chains work is you can drift a lot in V, but you can also have a risk of drifting a lot of you from your region of ellipticity. Remember, still rho phi is in front of the Laplacian, so it's degenerate. But in kinetic equations, time versus x versus v scale like lambda squared versus lambda cubed versus lambda, right? So if you move epsilon times n, if you do a lot of little steps in v directions, you only do epsilon cubed times n steps in x direction, and only epsilon squared times n steps in the time direction. So you can move a lot in v directions while barely moving anywhere in x and time. So that's why you still stay in your domain of ellipticity while reaching all the remote regions in a kinetic variable. So that's the idea behind these constructions of Harnack chains, and when you do this carefully, trace all the constants, you connect them all to the initial entropy, and the initial entropy is decay. So And that's all I have to say. Thank you very much.